So in section 4.5, we're going to use our rational polynomials and set them into equations and solve for x. So now not only do we have a fraction and a polynomial, but we're going to be solving for the x value that makes it true. And then we'll identify any extraneous solutions. That means like extra ones, or ones that might not actually work even though it looks like they do when you get done solving. So first thing, we could solve this. We're looking for our rational polynomial here, and we want to know what x value, there's our rational polynomial, what x value would make this equation true. So one option that you can do is called cross multiplication. So you could write 1 over x plus 4 and set it equal to 2, which is over 1, because that is our 2 as a fraction. When you cross multiply, you would have 2 times x plus 4, and the other one would just be a 1 times 1 here. So we'd simplify, we'd have 2x plus 8 equals 1, and subtract 8 from both sides, and we'd get 2x equals negative 7, and our final answer, if we divide by 2, x would be negative 7 halves. Now, you can do that when they're nice and simple like this. It's probably your easiest way. I'm going to go to the try it and look at another way you can solve these. So again, you can do that cross multiplication. I'll go ahead and do one of those in a minute like that. But another thing you can do is get a common denominator. So in this case, normally 4 is over 1 here. Well, if I wanted to get a common denominator, I would need to multiply by x plus 5. And whatever I multiply the denominator by, I'd need to multiply that numerator by it. So I'd have 2 over x plus 5 equals 4x plus 20, and that's because I'd multiply that 4 through, all over x plus 5. Now, this is kind of a weird thing to think about. In some ways, you can just remember that the denominator is going to disappear. But what's really happening is if you take this side times x plus 5 again, that would cancel out the denominator. It's also going to cancel out this x plus 5, because if what you do to one side, you have to do to the other. So essentially, you'd have 2 equals 4x plus 20. Now we're going to subtract 20 from both sides, and you'd get negative 18 equals 4x, and then divide by 4, and we would have x equals a negative 9 halves, or 4.5. So when we get done with these, again, you could have done cross multiplication. And if we did that real quick, let's just start this one over just so you can see the answers are the same. We'd have, oops, not 2, but 4 over 1. So I am just doing the same part A again to show you that they are matching. I'd get 2 times 1 is 2. Equals 4 times x plus 5. 4 times x plus 5. And that would mean 2 equals 4x plus 20. And I'm going to stop right there, because if you take a look, this is the exact same thing as this one. So we know they'd come out the same. Again, you can do cross multiplying, or you can get a common denominator. So over here, I'll do this one quick. If that was over 1 and I cross multiply, I'd get 2x minus 14. Don't forget to multiply the 2 by the x and the 2 times the negative 7. And then equals 1. If I add 14 to both sides, I get 2x equals 15. And dividing by 2 leaves x equals 15 halves, or if you like to put that in a mixed number, 7.5. Now we'll skip example 2 in section 4.5, but for example 3, now we still want to solve an equation, because you have the equals here, of rational polynomials. That means we have fractions again with variables. So we still would want to use a common denominator. We can't use cross multiplication anymore because we have 3 terms. So you can only do cross multiplication with 2. Just like we did with adding and subtracting, each of these needs a common denominator. So x minus 3 is needed on this fraction, and x minus 5 is needed on this one. So if I multiplied this through here, I'd have my 1 times 3 and my 1 times x. I'd get 1x minus 3 plus, multiply this x through, I'd have x squared minus 5x. And this last fraction had both those common denominators of x minus 5 and x minus 3, so I would be done. Now, we could write that all over. Gets a little redundant here, but I could put x minus 5 and x minus 3 down here, and x minus 5 and x minus 3 down here, right there, and x minus 5 times x minus 3 down here. The trick again is, just like when we did the smaller two rational polynomial examples, the denominator is going to go away, and here's why. Let's call our common denominator star, okay? So I've got 2 over star, and this x squared minus 5x over star. I'm just using a symbol because I don't want to rewrite all those factors. If we wanted to see how this is going to just disappear, it's not really magic, it's math. I don't want a denominator, so if I multiply this by star on the top but not on the bottom, these stars will cancel. But what I do to one side, I have to do the other. So if I were to multiply this whole thing by star, he would actually go through to both of these. I'd have a star there and a star there. Those would just cancel. So I am left with x minus 3 plus x squared minus 5x equals 2. It's all right just to have that denominator disappear once you've found the common denominator and multiplied these numerators by it. But now we want to combine our like terms and solve. So I'll move up here. We've got x squared. I'm going to write that x squared first because it's a highest power. Then I'm going to combine my x's. I've got an x right here, take away 5x. That'll be minus 4x. And then I have the subtract 3. That all equals 2. This one's a little different, and especially different because you have the x squared. In this case, whenever you have an x squared, you want to get everything to the same side. So I'm going to subtract 2 from both sides. And that gives me x squared minus 4x minus 5 equals 0. Now, when I get to this point, guess what? We get to factor. You could guess what numbers you could plug in for these x's and make it equal 0. But if we factor, we know x minus 5 times x plus 1 is the factor. That's because x squared plus 1 minus 5 makes negative 4, and then a negative 5 times a positive 1 is a negative 5. This would mean right here, if I put a 5 in, it becomes 0. And right here, if I put a negative 1 in, it becomes 0. So right there, normally we'd say, hooray, we found our x values that make this equation true. But what we need to double check is, this is where an extraneous solution comes in. We first found our common denominator, which I didn't mention the steps, but that's what we did. Then we simplified by getting rid of that denominator and then moving everything to the same side because it was a quadratic. As we solved that, we think our answers are x equals 5 and x equals negative 1. But go back up into your original denominators. Any of those x values, if you plug them into the denominators, they better be an okay value to do so. Remember when we talked about domain? What x value right there would go in and be a problem? The domain would say that x cannot be 5. And of course, it can't be 3, and those are the two values it can't be. But since x cannot be 5 in the original, this value of our solution that we thought it was is called an extraneous solution. That means the only real answer in this rational polynomial equation is x equals negative 1. So with these ones, it's always important to go back and check if that x value is acceptable in your original equation. Okay, so it's the same thing there. But extraneous solution, it's a possible x value solution that is not in the domain. So you just have to go back and check if it would work in that original rational polynomial. So if we look here finally at example 3's try it, notice how we have x plus 2 and x minus 2 and x plus 2 and x minus 2. This fraction is going to need the x minus 2 multiplying both on the top and the bottom, and this fraction is going to both need to be multiplied by x plus 2 on the top and the bottom. I love this example because it's just 1 on the top. So 1 times x minus 2 will be x minus 2. Plus this 1 times x plus 2 will just be x plus 2 equals 4 because he already had everything. Remember, my denominator is going to go away because if I had, remember if this was star and I multiply by star, all of those are just going to cancel. So I'm just going to go ahead and combine my like terms. Very nice this time. Nothing has x squareds even. So x plus x is 2x. Negative 2 plus positive 2 is 0. I get equals 4. And then I go ahead and divide by 2 on both sides. And I'm like, this seems nice. X equals 2. We're done. We need to check though. Will that work in the original domain? Go back and look up in your original values. They're a little tricky to see here. If I erase all that stuff and look at the original denominators, remember that's what tells us about our domain. This 2, if I plugged it in right here, or right here even, 2 minus 2 would be 0. This is an extraneous solution. So that means if he's not an option, nothing is. So if x equals 2 is extraneous, there are actually no solutions on this one. For example 4, it's pretty much the same thing. They just give us a whole number here. Remember this whole number 7 is like over 1. So we would say, well, that does not have this common x minus 2. So let's give it that by multiplying by x minus 2 on both the top and the bottom. So the 5x would be the same because it doesn't need any more to its denominator. We'd take 7 times the x minus 2 because that needed that common denominator and add 10. I'm not going to write the denominator anymore because it would actually simplify out. Since they all have it, we could multiply by it and it would go away. So we'd have 5x equals 7x minus 14 plus 10. We'd have 5x equals 7x minus 4. Add 4 to both sides. Oh, let's not do that actually because it will have nothing to combine with. So we're going to go ahead and subtract 7x from both sides. So if I subtract 7x from both sides, I get negative 2x equals negative 4. And dividing by negative 2 means x equals a positive 2. But oh no, we try to plug it into our original denominator. It's extraneous. So we would say there's actually no solution because that solution we did find doesn't work in the original domain. Lastly, we'll do one of the try-its. Here on part A, x is over nothing, so we'll put it over 1. Both these last terms have the x minus 3, so that means both of these numerator and denominator on the first term need to be multiplied by x minus 3. That means I'll have x squared minus 3x, because that x would distribute, equal or plus 6 equals 2x. I'm not going to write that denominator because it would reduce and go away anyhow. So I'm going to have x squared minus 3x. Actually, let's say that's minus 5x because I'm going to go ahead and subtract 2x from both sides. I have no terms to combine. So I'd have minus 5x here plus 6 equals 0. When you have a quadratic, it's time to factor. So x, let's say minus 6 times x plus 1 is a good factoring because that makes negative 6x plus 1x, and that'd be negative 5. So my solutions here, in this first one, I could plug in a 6, x equals 6, and the next one I could plug in negative 1. I think those are my answers. I need to double check. Do they both work up here? In the denominator, nothing is going to cause the domain to be undefined. So we would have both of these as our solutions. No extraneous this time.